writing a rule for these exponential functions, just like yesterday, we're going to fit our general rule here with our y is equal to an initial value times the base to the x power. So that boils down to finding two things. First, we need to find the initial value, which is the y value when x is 0. And we need to find the pattern. How is y changing as x goes up, as x changes? As x goes up by 1, how does y change? You have to look at the table. Anyone that's going to be a brave soul and volunteer what's happening here. As y goes up, what's x doing? Kaylin? So y is increasing by a factor of 5?
Decreasing.
Okay, it's decreasing. So what are we doing to the number to go from one number to the next? Dividing by 5. Yeah. So involving 5, and that same way, decreasing by a factor of 5, or dividing by 5. Okay. Yesterday, our pattern is all about multiply. Does anyone recall how to change a division problem to a multiply problem? We had like a catchy little rhyme that went along. Yeah, we said flip the second guy and multiply. Flip was the key there. If we want to change the division to a multiply, we'll flip. So when we write our pattern out, it involves all this multiply. We're going to plug in these things. The initial value, when x is 0, y is 1. Exponents are a bunch of multiplying. So I can't plug a division idea in for an exponent because that's a multiply. So if I want to, instead of dividing by 5, that's the same as flipping and multiply. So if instead of dividing by 5, what am I multiplying by? What would I multiply by instead of? 1/5. The reciprocal of 5, which is 1/5. Okay. So if you notice that your pattern is division, pick that number out and then just multiply by its reciprocal, or flip it in this case. So we can write our rule in much the same way we did yesterday. What's the pattern in our second one here? Are we dividing? Are they getting smaller as we go, as x gets bigger? No, they're getting bigger. Okay, so 4 is involved for sure. If I go from 2 to 8, if I go from 2 to 8, I think the giveaway. I'm multiplying by 4. Multiply. You may be tricked in division because there's fractions here, but notice as x gets bigger, the fractions are getting kind of larger as well. So this is actually a multiply idea. But your factor was absolutely correct. The initial value is when y is 1/2. So plugging in the things we know, initial value is 1/2. Pattern says multiply by 4. Okay. Try not to fall for traps that they'll set for you by throwing in some fractions. Just because there's fraction doesn't necessarily mean it's division. You have to kind of see how it's trending. Okay. Anyways, just like yesterday, we're going to graph these decay functions. A little bit different than yesterday, we're going to identify what's called the domain and range as well. So that's the one new thing we're going to add. And also, oh boy, I'd also like to show you how to use your graphing calculators to create these tables a lot more efficiently. Okay, we can do. Let's try to get this first. I want to do this first on my hand because knowing how to do this by hand is important. Okay, so I'm going to choose my independent variables here. Let's go in -2, 1, 0, 1, and 2, kind of our standard independent variable set. We'll plug in when x is -2, y is 1/3 to the -2. Well, what's 1/3 to the -2? Same as 3 to the +2, 9. When x is -1, y is 1/3 to the -1st, which is 3. When x is 0, anything to the 0 power is 1. When x is 1, anything to the first power is just itself. And as we saw yesterday, writing these as decimals can be helpful when we're graphing. And similarly, when x is 2, then y is 1/3 squared, which is 1/9, which is 0.1 repeating. Okay. Graphing these, so we graph these points. -2, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 is somewhere up here. -1, 3. 0, 1. 1, 1/3. 2, 1/9. And if I draw my exponential curve here, I think as Jack noticed earlier, that since we're raising fractions that are less than 1 to various powers, as you multiply them by themselves over and over again, you get smaller and smaller and smaller numbers, or they decay as x gets very big. So the same reasoning as yesterday, as this exponent gets really large, we're just going to create fractions that are like 1 over huge numbers. So we create really small fractions, but they're never going to be negative, and they'll never actually get to 0. So we, again, like yesterday, we have an asymptote here when we have y equals 0. It will never cross or touch this line y equals 0. You get close, but not really ever. It will never touch or get there. So that brings us to this idea of domain and range. I said D and R. Oh boy, do we remember the words domain and range from way back? Yeah. When we were talking about domain and range. It's been a while since we talked about domain and range. We haven't looked at functions in a while. Domain, what does domain go along with? X's. They're the X's you're allowed to plug in. And similarly, range is the Y's you're allowed to get out. So I'm asking you to describe what X's we're allowed to plug in. Well, let's see. Are there any numbers you're not allowed to plug in for X? Are there any numbers you can't have as an exponent? Have we ever talked about any of those? Are there any? I don't think there are. I think you're allowed to pick whatever exponent you want. Doesn't matter. So if you're allowed to choose any number whatsoever to plug in for X as that exponent, then your domain better be which, if you remember, we had this kind of sweet fancy symbol for all real numbers, the set of all real numbers. You're allowed to choose anything. Maybe an even cooler, maybe another way to write this is like an inequality. Might be like from negative infinity to positive infinity, you could do. Or just anything. X can be any number you want. There's no restriction on what real number you're allowed to plug into this exponent. Anything you want, we'll make it happen. Okay. Are there any y values then? Once we graph this, are there any numbers we'll never get in this y table? Are there any numbers that this graph will never get to or ever be? Yeah, it'll never be negative for sure. That's why there's an asymptote here. We said there's an asymptote. So there's an asymptote here at y equals 0. This graph will never cross or touch this line. So if it's never going to cross this line y equals 0, it means it's probably never going to be smaller than that. Or conversely, where will it always be? What y's will we always be kind of in? All the positive ones. So anyone know how to represent all the positive numbers? Positive numbers are numbers that are bigger than 0. So we can get any positive number out, but we'll never get 0, we'll never get anything less than 0. And again, the reasoning is that if we look at the graph, one of the ways we can see that is we look at the graph, it always flattens out right at 0. It's never crossing this asymptote, so it can't ever get below it. Can't ever touch it, it certainly can't go below it. So our range has got to be anything, or the y values we could possibly get are all the stuff that's above it, or any y that's bigger than 0. Let's try to do the next one, but quickly show you how to use your graph calculator to do it more efficiently. If you have a graph calculator, please get one out. If you don't have one, then hopefully you can either look on with someone that's next to you at your desk, or worst case scenario, you can follow along with what I'm doing up on the front here. But I want to show you maybe a more efficient way to come up with these table of values than just doing everything plotting along by hand. The graph calculators do a lot of really cool things. First of all, one of the main things they do is graph. And in order to graph, we make tables of values. So does your calculator. So your calculator is really good at making tables of values. If you hit, let's start by hitting the y equals button. And it brings up a screen like this. And I want you to type in the function that we're going to try to make a table of. So in this case, y equals 0.4 to the x, or type it just like you see it, parenthesis, 0.4, parenthesis. I want an exponent, so I'll hit the caret button. On my TI-84, it brings up this fancy screen. On the TI-83s, I believe it just is a caret. It just has the upside down V. And then I want what's in the exponent is my variable x. So to make an x, if you're not familiar already, we can hit this button on the TI-83s and 4s. It has an x, t, and a couple other symbols in there. We'll hit that, and that'll give us an x.
Wait, how'd you do that?
Okay. To repeat, I'm going to make an exponent. So I hit the caret button. That gives me an exponent. After the exponent, I want a variable. In this case, I want an x. The x is located next to the alpha key. It's got 4 letters written on it, x, a t, and then 2 other symbols, right next to the alpha key. If you hit that button, that'll pull up our variable x that we want. Okay. On my TI-84, it displays something like this. On a TI-83, can I borrow someone of the TI-83? On a TI-83, your display will look like, oh boy, it's kind of hard to see. On a TI-83, your display will look something like this. There's the caret and then the x. It's the same thing.
Mine's a TI-84, it still looks like that.
Good. So on some of the 84s, it does that. Before we look at, well, I guess we don't really need to. From here, once we have it typed into the y equals, we want to look at a table of values. So if you hit second and graph, it'll pull up a table of values. And most of you are defaulted to make what's called to auto choose the x's. Notice that there's a bunch. On mine, I started at 8 for some reason. I don't know why.
Wait, what did you press?
Hit second and graph. And that brought up table of values. Notice that, like, I'm getting some weird numbers over here. You can, if you take your cursor, you should be able to scroll up and down and maybe get to x's that you want to find. So, like, we're trying to graph, like, for our case here, we want our x's we'd like to choose are our standard ones, -2, -1, 0, 1, and 2. If you scroll up and down on in your table of values on your calculator, when x is -2, y is 6.25. When x is -1, y is 2.5. And we can fill in our table pretty efficiently here. Okay. Did anyone have troubles with doing that? Once they're plotted, we should get 1, 2, 3, 4, 5, 6 and a quarter, -1, 2.5, 0, 1, 0.4, 0.16.
Is it 0.0?
Which one? Here?
Oh, just one.
Yeah, anything to 0 power should be 1. What's the domain? What x's are you allowed to plug in? Has anything changed from before?
No.
Other than the base? No, but there's still, we're just plugging in x's to an exponent. You can still pick any number you want. We still can choose any real number for x. And what y's will we get out? Will y ever be negative?
No.
Okay, will y ever be 0? No, it never touches this line. So it's anything above that. Or
The main range always be the same thing.
for our purposes, unless we start doing some weird things to this, like, well, if we reflect it, then we have, if we multiply by a negative number out front, then we've reflected it, so now we're going to have only negative numbers. The only time the value will change from 0 will be if we what's called shift this, vertically shift it, and that would, you'd have to do some other kind of crazy things to this function, which you'll do a lot more of in Algebra 2. We're not going to focus on that here. Okay.
Sooner or later.
Let's try to use our graphing calculator like we did like we just did to efficiently fill in this table of values. And if at all possible, I want you to graph these. And like we did yesterday, we're going to compare. We're going to use the same comparison words. Do we recall what the comparison words are we're going to use? We have 3 phrases. Remember the first one. What's one of them? Someone's got to have one of those comparison phrases. Oh, check your notes. This is open note too. Joe? Vertical stretch was one. Vertical shrink is the second. And reflection is the third. So if we have those 3 things, let's graph each of those functions, please. We're going to compare these 2 to the third one. This is going to probably be the most important thing that we do, is being able to take a graph and make a reasonable conclusion and decide what's different about it. Compare, using words, what is different from the original. Okay, we're going to be using this idea to kind of build more and more, and as you move on and on through your high school career, all of you will be taking 4 years of math before you leave this building. You're going to be doing a ton of comparing. We want to build on that starting now. Okay? So if I were you, I'd use your graph calculator to create these tables efficiently. So if I go back to y equals, I clear this one out. If I want to raise 1/3 to the x power, I'll type parenthesis 1 divided by 3, parenthesis, to the x power. And second graph to make a table. And just like I had, I can go through and fill in my table for my first guy pretty quickly. 9, 3, 1, 1/3 or 0.3 repeating, 1/9 or 0.1 repeating. You can go back to y equals, and if you can either clear this and retype it. If you're savvy, calculator savvy, you'll hit second delete to insert something, and I'll insert this 2 that's being multiplied. And look at the new table. And now, in my case here, if I multiply by 2, or you just do it all by hand, 2 times 9 is 18, 2 times 3 is 6, 2 times 1 is 2, 2 times a third is 2/3, which is 0.6 repeating. 2 times a ninth is 2/9, which is 0.2 repeating. And lastly, you could go to the last column, and instead of multiplying by 2, this time multiply by -1/2. So take all these values and multiply by -1/2. You could also, again, go back to your graphing calculator, clear this out, and go -1 divided by 2 times, parenthesis, 1 divided by 3 to the x power. Pull up your table. -4.5, -1.5, -0.5, -0.16 repeating, 5 repeating. And we can graph each of those. Algebraically, what should the comparison be of this to its parent function? Without even looking at the graph like we did yesterday, how should this function compare to the parent? What's different about this one than this one? Multiplying by 2.
It'll be stretched.
So I'm stretching it by how much?
2.
A factor of 2. So without even graphing this, we could see that this is a vertical.
As the bell rings, please direct all juniors whose last names begin with the letters L through Z to the Media Center for ACT bubbling. If they have a number 2 pencil, please bring it along with you. All juniors with last names L through Z to the Media Center after this bell. Thank you.
Since we're multiplying by a number bigger than 1, that's got to be a stretch by a factor of 2. Namely, likely, same as yesterday, we're multiplying by a number less than 1, so this is a vertical shrink. We're cutting everything in half, and it's negative as well. So it's also a reflection. Okay, and you can see that very visually if you graph each of those. Plot each